Well, good morning, everyone. Let's go ahead and get started. So today, before we begin, just a couple of things. So first is I had a couple of people asking the sort of same question about the waste audit. I just wanted to address this for everyone. So the idea being here is, if you have, X number of corrugated cardboards, you threw 5 in the trash bin, 10 recycle. Well, actually, I'm going to make the math easy. 5 and 5, and 0 here. 3% recycle would be 50%, right? Or 5 divided by 10, right? Or 50%. Now, that's pretty straightforward, and you want to do this for everything. You want to make sure you fill out this table in its entirety, just so you see the numbers. And this sort of percent recycled here is pretty important. This is really the most important part, right? How much are you recycling of your total trash? Now, as you go down here, you go to the end, you get to the total. Now, the totals, this column will essentially be the sum of everything above it, the sum of everything above here, and sum of everything above here. That's what we're looking for, the totals. And so when you calculate your percent recycled, it would be, if you had 50 here, 0 here, well, that would get you back to that 50%. So that's really what it's looking for. I just had a couple people got confused on that. I just wanted to sort of clear that up with everyone. So, and the other thing is make sure you answer all the questions. For instance, like this last one, it's 3 to 4 sentences, not something you can answer in a sentence, right? Looking for much, much more. And just make sure you answer all the questions in their entirety, so that you get all the points, right? And then the second thing is I graded all your papers. If you have any questions, please let me know. If you haven't turned your paper in, you have till tomorrow night to turn it in, unless you have the excuse, valid excuse, as we have discussed before. So you definitely don't want to not turn in your paper. It's worth 35% of your grade. So at least getting half that 35% is will help you do well. So. And then it's just, I guess, as a final note, make sure you again review your grades. Keep on top of what you're doing. Ask me any questions. Let me know. I'm here to serve you guys. That's how it works. And don't be afraid to tell me I'm wrong. Don't be afraid to question my grading. Just let me know. Because I grade things and you might not see things differently, or I might have been too hard. There's just all sorts of things. So please check your grades. Please let me know. Please don't wait till the last minute on grades. It's one thing I can't stand is people waiting to the last minute for their grades, because that's a pain in the butt to change. But with that out of the way, let's get into the topic of the day. So it's going to continue on sort of thinking about what we were thinking about last class, thinking about public health. And one sort of aspect of public health and disease make your own informed decision based on that. But again, this is all just the science, no opinions from me. And as always, if you have any questions along the way, please ask them in the chat or scream them at me, as you all know at this point in time. We're 20, was this class 22, if I'm remembering correctly? So, you should be pros at asking questions in class now. Before we get started, you should have received a notification in your UMass email about course evaluations. Please do them. And I say please do them, not because I want you to give me good reviews, not because I get a bonus or a raise or anything like that. I won't see these reviews till like October, so they don't affect your grade at all. But simply, please take the 5 to 10 minutes to just sit down, do this, and let me know. Let me know what I could do to improve topics, ideas about my teaching style, the resources, the assignments, whatever whatever you sort of saw in this class that you didn't like, whatever you did like, let me know. Because I genuinely want that sort of feedback. I want to know how I can make this course better as I teach it through time. Simply because I want this to be the best, sort of the best I can make it. And if I need to modify how I teach, how I make slides, how I do anything, or the assignments or the workload or whatever, please let me know. Or if you hated it, let me know that too, so I can try to make it better for the next group of people that teach it. So I'm not teaching it this fall, but I'll likely teach it next summer and next spring as well. So, I'm definitely going to incorporate what you guys say. I always do. So, All right, so with that out of the way, let's let's dive into the thing. So I wanted to give you sort of this cool science in the news I picked up. I did actually, this came out last year, but I actually didn't see that till recently. But it's really sort of uh, really important to today's lecture because, as you can see, it's measles and immune amnesia. If you want to take a peek, this is a press release from the American Society of Microbiology, one of the best resources out there for microbiology as a whole. But if you had a chance to take a peek at my measles slides I dropped into the class PowerPoint section, you'll know that measles is one of the most contagious infections on the planet. So much so that if we were all in class together, all 35 of us, and one person had measles, all but 2 of us would get measles. So it's super duper infectious. And it's been that way essentially throughout its history as a disease. And it's a disease that's been around us for varying levels of time, depending on who you ask, but at least 10,000 years. So it's been around for a very, very long time. In the United States as a whole, we've successfully eradicated measles from us with the MMR vaccine. It's present across the world. When I say when the United States had eradicated measles, I mean like we had no local transmission. So like everyone that got measles in the United States, they got it from another country. That's not the case anymore. We're not eradicated because of anti-vaccination movements, but one of the things that's sort of interesting about measles as a virus is it's sort of systemic. It doesn't just stay in one spot. It doesn't stay in your skin. It kind of goes everywhere, right? It goes to your brain. It goes to your lungs. It goes everywhere. Measles is like COVID in that way. It just kind of takes a walk around your body. One of the things that's interesting is they've found this sort of this really weird phenomenon with measles, and as far as I can tell, they haven't observed it in any other disease. But this brand new study. In non-human primates, so you think about chimpanzees and stuff like that, that sort of showed that the measles virus actually can replace your memory cells in your host. And one of the sort of interesting things that means is your memory cells allow you to remember a disease you had. So if you had the flu from last year, your memory cells make it so you can't get the flu next year. That same exact flu. So the flu in 2019, you won't get it again ever again in your life because your memory cells. Measles, in all of its jerkiness, which is vaccinated. So this only happens if you get measles. So this doesn't happen if you're vaccinated. But if you get measles, it can erase your memory, making you more susceptible to other pathogens and even other pathogens you are vaccinated against, which is sort of an unfortunate thing. And they note that it takes about 2 to 3 years post-measles infection for your protective immunity to be restored. So measles, all the terrible things it does to your body, it comes in, wipes the slate clean of all your other disease immune responses to make you more susceptible, which, again, icing on the cake for a really terrible disease. So with that out of the way, I just thought I'd show you some cool science around this, and I got some cool science for the next couple of days too. But the topics for today is a brief history of vaccination, how they work, the different types, what are the side effects, how they're made and approved, and stuff that's not true. And so just as a note, if you need some resources on vaccination, there's a lot of really bad resources out there. Very much like I mentioned with COVID and really all the other topics we've talked about through this course, but in particular ones that have become pretty heavily politicized. There's lots of bad resources out there. So if you see something on Facebook, if you see something on Instagram, if you see something that's not in a really reputable source like the World Health Organization, the CDC, the FDA, a major hospital, take it with a huge grain of salt. And if you want to know the real information, you could come to my slides, I guess, but you really want to consult the experts on this. People at the Mayo Clinic, the American Society for Microbiology. If you're interested in pets, the American Veterinary Association will tell you all you need to know about pet vaccinations as well. But again, lots of bad information out there. Go to reliable sources, UN, FDA, so on and so forth. These are all great resources. But again, anything that's not from a .gov or a .edu or a .org, or at least a reputable .org, will be not the best. So With that out of the way, let's give some quick definitions. So a vaccine is a biological preparation that improves immunity. And improves immunity to a particular disease by containing agents that resemble or are actually that specific disease-causing agent. And it does this to stimulate your own body's immune system, to develop long-term immunity. So that's a vaccine. That's what it's supposed to do. Now, vaccination is simply getting a vaccine. When you say immunization, it's the process in your body after you get a vaccination. So when you get the measles vaccination, the process of your body becoming immunized to measles is basically immunization. That's what we're working with here. So in terms of vaccines, it started much longer ago than most people think. It started in late 1700s, and it was all led by a physician, Edward Jenner. And he worked on one of the most infectious diseases of all time, smallpox. And he worked on smallpox's less deadly cousin, cowpox. Now, smallpox, as we talked about, was eradicated in this planet in the 1960s. It, in the 20th century alone, it infected 50 million people, killing 2 million. And so throughout time, it's been one of the most infectious and deadly diseases out there. It depending on, where you look, it has approximately a 30% mortality rate. So it's a pretty high mortality rate. And this disease has been around for a long time. It's basically been around since we invented agriculture, so about 10,000 years at this point. Smallpox and its friend cowpox is caused by a virus. As sort of we mentioned, it was eradicated worldwide in the 80s by the World Health Organization by vaccination. And smallpox, as I mentioned, has a very close relative called cowpox. And this becomes important because, as I mentioned, smallpox is really, really deadly. And so you could think back in 1796, it would be really hard to work with a very deadly pathogen, right? Nowadays, we have all these great technologies to prevent scientists from getting infected and doctors from getting infected. But back then, they didn't have any of that. And so he needed something that he could work on to understand smallpox without dying or without people dying. And so what he turned to was the relative cowpox. And cowpox looks a little bit like this. So this is a really old picture of a textbook, or not textbook, just like a leaflet. And this is what cowpox looks like. It's just basically like little pustules that form on the udder of cows. Now, Edward Jenner lived in an agricultural community, and he was aware of this folklore that existed both in where he was living and throughout Europe, that milkmaids never got smallpox. Now, what he did know, and what everyone knew, is that milkmaids did get cowpox, which is, again, a cousin of smallpox caused by a virus, but that you get it from cows. And again, it looks very much like this on the cows. Now, if you look at the sort of the grouping phylogenetically, we have what are called the orthopoxes, and these are a group of viruses that affect all sorts of different types of human pathogens, including cowpox, vacina, monkeypox, and variola, which is our smallpox. Now, what you can see is under this orthopox label, we have cowpox, and they're closely related to our smallpox. And that becomes important. They're closely related. And remember, in evolutionary terms, things that are closely related have many more similarities, right? The finches on Darwin's Island were different in respect to certain characteristics, but overall, they had very similar characteristics of traits, right? So the same thing happens with the viruses. Cowpox look very similar to smallpox. And that's important. And visually speaking, as you can see, this is a child unfortunately infected with smallpox. You can see that smallpox looks a lot like cowpox, right? If you sort of go back 2 pages, we see the udders here, right? Cowpox looks a whole lot like smallpox. So given milkmaids never getting smallpox, given the similarities, given the evolutionary significance of this, Jenner asked the question, was the relationship between the two viruses? Because he knew milkmaids never got smallpox, but they did get cowpox, so was there a relationship? And so Jenner devised a really simple experiment. So what he did is he took a woman named Sarah Nelms, and she was a milkmaid infected with cowpox. And then she took a young boy, James Phipps. He was inoculated with cowpox from the pustules growing on the sores on Sarah Nelms. So this boy got infected with cowpox. He got a very mild case of cowpox because, as I mentioned, cowpox causes disease, but it's very, very mild relative to smallpox. So And he intentionally inoculated this boy with cowpox, a non-deadly disease. So it'd be like, me giving you guys, giving someone in class the cold, right? You're not likely to die from a cold, right? And you're certainly not likely to die from cowpox in this case. A little bit unethical, right? Willingly infecting a child, but this is back in the 1700s, so it was a lawless time, I guess. Um, and so that's the setup, right? Infects a child with smallpox. Now he takes a woman that has smallpox, he collects her pustules and inoculates the young boy. And remember, this young boy was infected with cowpox. Interestingly enough, this boy never develops any symptoms of smallpox. And all because he was protected by cowpox. So what the heck is happening here? He got cowpox, he now can't get smallpox. And this flow of information should sound like a vaccine, right? If I get the measles vaccine, I then, if I'm exposed to measles, should not get measles. And so I hope this workflow is sort of clear in that, well, this is what vaccination looks like. So the idea here is the body's immune system was trained to recognize cowpox because the boy got cowpox. And because cowpox and smallpox are so closely related, and again, they had very similar traits, it was able to recognize smallpox and got rid of the smallpox infection. It made the person immune. And again, this should sound history of vaccines that developed after. It took about 100 years for this a real meaningful vaccination program to take off. But once it took off, there's many, many, many types of vaccines that have come to be. And now, if you sort of look at a timeline from here, again, we have Jenner in 1798, and you'll notice there's all sorts of vaccines that have been developed over the past 200 or so years. And there's any number of diseases that you can think of, right? You can think of tetanus, influenza, yellow fever, pertussis or whooping cough, right? All these diseases we've developed immunizations for. And that's a really huge testament to the development of science. If you're interested in any of this sort of history of vaccination, I would recommend you take a peek at this paper from Nature. It's a really nice sort of reflection about the development of vaccines over time. It's a really nice read. And that's what this figure is from. But what you'll notice is that these sort of got more intense as time went by. We're seeing more developed as technology got better, as we better understood the microbiology, as we better understood the evolutionary history of these organisms. And what you'll notice is that some of these diseases are horrible. Rabies, tetanus, horrible, horrible diseases that we can now keep in check with vaccination, right? But you also notice that some of these diseases are still present, like cholera. We have a vaccination from it, but we still get cholera out there, right? But you also notice that some vaccines were improved. So influenza has been improved multiple times. Measles vaccine was improved 3 times before modern times, right? So vaccines are improved, they get better. And it's an important thing because as we improve our vaccines, their efficacy increases. The more people will get them, the cheaper they get. And so we can sort of look at sort of how things go. We have deaths per 100,000 people, and these are from infectious diseases. So this is what we have in green. And then we have the life expectancy in years. And you'll notice that the life expectancy is going up and up and up, much, much higher, right? From 50 all the way up to 70 in the 70s by the time I reach 2000. But you notice that deaths from infectious disease are tanking, right? We're on this sort of upslope again because of antibiotic resistance and HIV and even COVID as well. But what you notice is that as vaccines really took off, you can see some of these being developed in the early 1900s. As these vaccines took off, infectious disease and deaths from them really tanked because vaccines are really good at preventing diseases because they use very basic biology from your immune system to protect you long term. And that's important because, again, smallpox has killed hundreds of million people. The Black Plague killed hundreds of millions of people, right? Diseases kill lots and lots of people. And the other thing that these vaccines are important for is essentially to protect against antibiotic resistance. So if we just go back a couple slides, you'll see cholera, right? You'll see some other ones, right? Tetanus is a bacterial disease, pneumococcal, so pneumonia. right? So you're seeing all these bacterial diseases. And now you might think, well, if I have a bacterial disease, let me take an antibiotic. But as we talked about, as we introduce antibiotics, we're seeing antibiotic resistance. And we're essentially approaching an antibiotic apocalypse, right? Where antibiotics are no longer going to be effective. But the important thing about vaccination is if I have, say, a cholera infection, right? If I had a vaccination against that, well, I no longer need to use antibiotics, right? Because I have my vaccination. And so vaccinations can help with this epidemic, this potential apocalypse of antibiotic resistance that we're currently sort of experiencing. So it sort of takes the burden off trying to develop new antibiotics simply because of how efficacious vaccinations are. But overall, you saw all those vaccines that were developed over time. The World Health Organization estimates, and this is backed up by multiple governments worth of data, that it saves between 2 and 3 million people every year. Some years are more, some years are less, but on average, about 2 to 3 million people lives are saved every year. And that's a lot of people, right? I mean, not relative to sort of the global population, but that's 2 million people that didn't have to die, right? And that's an important thing, right? Human life has precious value. And so vaccinations help to save that precious value. Vaccines to date protect against 26 diseases. Some vaccines we don't use anymore, but we use regularly about 26 of them to prevent 26 diseases. They help limit the spread of antibiotic resistance, as we discussed. And if we increase global immunization, we know that we could save even more lives. So vaccines are important. They have done a lot of great work. If you want to look at the numbers and sort of how effective they are against sort of kicking diseases down, like tampering down their incidences, we can look at sort of in the United States, so pre-vaccine area, estimated annual morbidity or mortality before vaccine and after the vaccine. And I hope the syringe is full of blood tells you, all these diseases see a significant decline over time. Things like diphtheria essentially don't exist in the United States anymore because of vaccination. Measles, you can see measles, 500,000 cases a year down to very low numbers, right? So you're seeing essentially a tanking of all these major diseases that can cause death or even permanent issues being eradicated by or extremely tampered down by vaccination. And so they really do work. The numbers don't lie. And this is the United States. You can look at any country on the planet that uses vaccinations, and you'll see the exact same trend. So they are really, really effective at getting rid of it. And you also have countries that don't have wide, robust vaccination programs. Particularly those that are doing less well off economically. You can think of like sub-Saharan Africa that don't have great vaccination programs, and you see these diseases running rampant. You see polio, you see measles, you see those things. But in places where you can get vaccines, they're really good at tamping them down. Now, that's sort of the historical perspective and the efficaciousness, the effect of vaccines on human health. Now, let's talk about how they work. What's the science that goes here? Now, the idea is with a vaccine, you're getting a dead or weakened form of the germ or a part of the germ. And we'll talk about the sort of the major classes of vaccines in a moment, but just to know you're always getting some part of an organism. You're not getting chemicals to become immune to it. It's always something biological in nature. Just that's a pretty common misconception. You don't get chemicals. You get some form of the organism, some safe form of this organism. And again, germs can be anything. It could be bacteria, it can be virus, it can be fungus, it could be microscopic eukaryote, it could be anything. But again, you're getting some sort of germ. You get that, it sparks your immune system to release and develop antibodies. And these antibodies not only will take care of that invader, but they'll also keep a long-term memory of that invader. So if you're ever exposed to that invader again, in a live form, your immune system will have the antibodies to recognize it and get rid of it. That's the idea. That's the workflow of how vaccination works. Exposure to a part of the organism or a very, very weakened form of the organism. You develop immunity through your immune system, and then you are immune to it going forward. Now, I just want to make note is your immune system is awesome. If your immune system was operating at peak efficiency, which no one is, your immune system could fight off anything. The human immune system is amazing. But the problem is humans the way we live are not amazing. You can think of the healthiest person you know, they exercise, they eat right, whatever. Their immune system is not operating at peak efficiency. So no one's immune system is that good. It has the potential to be, but no one's really is, because, again, human health is not perfect, right? We have pollution and all the stuff that knocks down our health. But which is why, even though we don't have a perfect immune system, vaccination helps us push us towards being more perfect. But the idea being here is it's a breakdown between what we call innate and adaptive immunity. So innate immunity is things that essentially, things that don't require any specificity, so that are general sort of antagonists towards microorganisms. Now, this starts off with your epithelial layer, so your skin cells. They act as that natural barrier. You might not think about it, but your skin cells, that outer layer of your skin is tough. It acts as your first line of your immune system. It's what we call your innate immune system, because it doesn't require any training to do its job. In addition to other parts of your innate immunity, you have what are called phagocytes, which essentially engulf and kill bacteria. They basically eat them alive, or viruses alive inside your body, but they don't require any specificity, as do what are called natural killer cells. Again, they don't require any specificity to do their thing. So that's your innate immunity. It starts with your skin, but it goes to much broad things like natural killer and phagocytes, things that don't need to be trained to kill that don't need to be trained to kill microorganisms. Now, that being said, you can sort of tell by this graph, or this figure, I should say, that this isn't perfect, right? Your innate immunity can't take care of everything. And this is where comes your adaptive immunity. And your adaptive immunity arises by exposure to some microorganism. Now, again, your innate immunity is generalized. It's good, but it's not that good. And so your body heavily relies on what are called your lymphocytes. And so these are your essentially your memory cells, or in the case of T lymphocytes, they're essentially more generalized, what we call killer cells. And a killer cell basically just kills the microorganism. That's really all it's designed to do, as its name suggests. Now, the idea here is if you're exposed to a microbe, your B lymphocytes and your T lymphocytes, they will modify their structure in response to that microorganism. If they modify their structure, they essentially take a part of the microbe, which we are calling an antigen, and they essentially tack it on to these receptors that exist on side of your lymphocytes. And this antigen gives them specificity. So this antigen will vary. So if you have something like cholera, the antigen for cholera will look very different than the antigen for, say, malaria, or tetanus, or measles, or HIV, right? It'll look very different depending on the disease you're faced with. But the key here is you modify your adaptive immunity to recognize specific microbes by essentially incorporating a small part of that microbe in your cells. And the cool thing about this adaptive immunity, it hangs around essentially forever. So if you get a measles vaccination when you're a kid, the antibodies that have the measles antigen hang around and are replenished throughout your entire life. And that's the cool thing about the adaptive immunity, is it hangs around for a long, long, long time. So this is how it works. It doesn't target this innate immunity. Vaccination targets your adaptive immunity. And it's sort of just as a last note about this, I mentioned measles can sort of wipe your immune system, and when I meant it could wipe your immune system sort of at the start of this lecture, I meant that it gets rid of your adaptive immunity here. But again, as I said, the cool thing about the adaptive immunity is once you trigger it, you're immune for a very, very long time, sometimes forever. But the thing about vaccination and why sort of less people vaccinating is kind of a big deal is vaccines, they work to protect you, but the thing that vaccinations do is they typically are better for protecting those that are around you, so those that cannot get vaccination. And so there's a pretty large group of people in any given population. This includes infants, young children, the elderly, people with severe allergies, pregnant women, and people with compromised immune systems that simply cannot be vaccinated. And so while your vaccination against measles protects you against getting measles, it's equally as important for protecting those that can't get vaccinated. And again, there's a pretty big group of people that simply can't get vaccinated. And the idea being is we rely on what's called herd immunity or community immunity, which I like better than herd immunity because community immunity rhymes. But this idea of herd immunity relies on the fact that if you can vaccinate enough people to any given disease, the pathogen won't have enough hosts to spread and will eventually die out from the population. Now, this is what happened with smallpox. We vaccinated enough people against smallpox, that there was just simply not enough hosts for smallpox to propagate to and spread through the population, causing smallpox to die out. And that's an important thing. We vaccinated enough people, we got herd immunity to a high enough level so that smallpox could no longer spread. And that's how this works, right? You need enough people vaccinated to make a vaccine effective. Again, your vaccination helps you directly, but it is important for a community or a global health perspective, right? When we get the coronavirus vaccine, if enough people don't vaccinate, it's simply not going to work to stop the spread between large groups of the population. And that's just sort of an unfortunate reality, is that you need enough people vaccinated to work at the population or the global health level. And again, this also helps to protect those that can't get vaccinated. And if you're vaccinated and 90% of people in Boston are vaccinated, actually, Boston is much higher. Boston is closer to 98% vaccination rate. That's because we're awesome. But if you have a really high vaccination rate in Boston, like we do, it means that it protects those that can't get vaccinated. And that's an important thing. Vaccination helps you, but it also helps the population as a whole. And again, it is good for your community. And so if you think about this really, really awesome infographic from Australia, you have any given disease, you have people that are in red here that are contagious, and those that are in yellow that are susceptible and not immunized. Now, the idea is that outbreak will be less. And so this is what herd immunity is. It's good for you, it's good for your community, it's good for those that can't get vaccinated. And the percentage for herd immunity varies between different countries and different diseases, but typically ranges between 83 to 94% of a given population. Some diseases like measles require about 92%, simply because measles is incredibly infectious. Other diseases require less. What that number is going to be for coronavirus, we have no idea. But given how infectious coronavirus is, it's probably going to be high in the 90s. So that's just sort of the principles of vaccination, how they work at the immunological level, how they work at the community level and the population level. Let's talk about the different types of vaccines. And there are essentially 4 different types, with the 5th one down here being the bottom is just being a combination. So let's talk about these different types of vaccinations, how they're made, how they work. So let's start off with live attenuated vaccines. And these vaccines are prepared from living but weakened microorganisms. Now, the idea being here is you take a virus, say in this case measles, you take it and you weaken it somehow. And you can weaken it a number of different ways. The most common way they weakened a measles virus is actually by injecting it into another organism and propagating that for a couple generations, like a couple weeks. And what will end up happening is the virus will mutate inside the new host. And what we do is we take a weakened form of that virus, so one that's better adapted to that new host, and we use that in the vaccination. That's how that works. So you weaken it by essentially making it adapt to another host, and then you bring it back, that weakened virus, back into the original host. That's typically how live viruses do. But the idea being is you keep them alive, but you essentially weaken them. So you limit how much they can replicate in the original host. So again, if I have the measles virus, I attenuate it, I make it replicate less fast, I make it less deadly. And by making it less deadly, it means your immune system can respond to it, right? If you took a normal measles virus, it's pretty nasty. It'll ravage your immune system. But if you take a weakened measles virus, like is in the MMR vaccine, again, it's live and attenuated, your body can process it in a much more efficient way. Now, so with that out of the way, the vaccine typically cannot cause any diseases, but there are very rare cases. It varies between the vaccine, but it's greater than 1 in 250,000 cases that the virus or bacteria can revert back to a pathogenic form and cause the disease. So the idea being is if you got a measles vaccine, there's a very low probability, it's about 1 in 1 million, that virus that you get in the vaccine can revert back to being a very bad form of measles and cause measles. But again, that's very, very, very rare. And the cool thing about this is it gives you very, very long, lifelong immunity. So once you get the measles vaccine, you're immune for the rest of your life. And again, it's because you're being exposed to a live virus. It's attenuated, so it is extremely weakened. It cannot cause disease inside you. It cannot kill you, can't really hurt you. It's weakened. So like, picture like, like you have a professional, have a professional golfer, and or a professional basketball player, and he's going to play against a fifth grade class, right? The professional basketball player is going to dominate that fifth grade class simply because relative to the professional basketball player, the fifth grade class is relatively weak in terms of basketball skills, right? So, picture LeBron James dunking on fifth graders, right? That's what a live attenuated vaccine is, right? The attenuated vaccine would be like the fifth graders trying to go up against LeBron James. Not going to go very well for those fifth graders. And so here's a nice little fact sheet. Again, it gives you a really, really solid immune response. The virus themselves are capable of replicating within the host cells, and they are living, but they're extremely weakened, which gives them a really good long-term immune response. Now, that being said, as I mentioned, they can revert back to the original form and cause disease, which could be potentially dangerous. But again, it is very, very rare overall. And it can cause some potential harm to those that are immunocompromised. So those that suffer from HIV cannot get a live attenuated vaccine as well. So there are some issues with here, but overall, it's a really good immune response. It's really effective. Again, a measles vaccine is a great example of this. We've been using it for 50 years with no issues at all. So that's our attenuated vaccines. Next up is our inactivated or killed vaccines. And these are organisms that are heat or chemically killed, and their dead parts essentially stimulate your immune system. And that's pretty cool, right? You kill a virus, you kill a bacteria, you inject it inside you in the most simple way. There's lots of science that goes on before that, but that's the idea. And it provides immunity. And now I guess not the cool thing, but the important thing to note here is that these vaccines typically require several doses, but they're generally lifelong after that. So this includes the polio vaccine, hepatitis A, and the rabies vaccine. These are just killed versions, so they can't cause disease because they're dead, they're broken apart. You're just getting like bits and pieces of these organisms, but you still have those bits and pieces, and your immune system will respond to those bits and pieces. For instance, if you ever got your hepatitis A vaccine, you would know that you got that multiple times. If you ever get bit by a bat or a wild animal, if you get a rabies vaccine, you'll get a bunch of rabies vaccines. But again, once you get multiple vaccines, it's lifelong immunity after that. So if you get your polio vaccine, you're immune to polio for life. And as we mentioned, there are with all vaccinations, there's down parts. The important thing about this essentially this killed vaccine, there's no live components, so there's essentially no risk to ever contracting the disease, and they are pretty stable overall. But the downside of this is they do provide a really good immunity in long term, but again, it requires multiple vaccinations, and this might not be ideal for countries, say like sub-Saharan Africa, that are taxed, economically, that providing multiple vaccinations isn't exactly the best thing in the world. But again, if you can get multiple courses of these types of vaccines, they work great long term, and they're very, very safe. Next up is cellular vaccinations, which is very similar to the one we just talked about. And this is the idea where the pathogen is broken apart and fractionated, and those fractions of the cell, so say, for instance, if we have a virus here, the outer coating of the virus is used as a vaccine. So you get rid of all the other stuff about the virus, you just keep one specific part of the virus, and you use that as a vaccination. Now, the idea is it's typically something that's on the outside of the virus or the bacteria, and as you likely saw in the adaptive immunity slide, your body recognizes the outside portion of viruses and bacteria. So you can take the outer portion of it, get rid of all the rest of the virus or the bacteria, and your immune system will still recognize that bacteria or virus just based upon its outside. Because remember, your cells are tagged, right? If I'm a liver cell, I say I'm a liver cell. If I'm a bacteria, I say I'm a bacteria. And your immune system can also recognize that. And so examples of these types of vaccines include shingles, HPV, as well as hepatitis B. And these ones do require 2 to 3 doses, but they do They do give you lifelong immunity as well. So, for instance, I was tested for Hep B immunity recently because I had a weird result on a liver test. It told me I was still hepatitis B immune, and I got that Hep B vaccine when I was about 8 or 9. So it's been going strong for 20 years as a whole. And again, there is downsides to it. There's no live components, so there's no risk of getting disease. It's very stable. It has a very long shelf life, which is good if you're trying to give it in a place where, for refrigeration is an issue. But the sort of the issues with this type of vaccine is you have to determine what specific part of your organism will produce the most effective immune response. That can be difficult at some time. And the other issue sometimes we see with these vaccines as they're being developed is if you don't get the right part of the microbe, you won't develop an immune response. So they are good, they're very safe, but it takes time to develop these ones overall. And then finally, we have what are called toxoid vaccines, and these are probably I don't know, I think these are some of the more interesting vaccines because they're some of the weirdest diseases out there, and these vaccines include things like diphtheria, tetanus, and pertussis or whooping cough. And these toxoid vaccines rely on the fact that pathogens, once they start to affect you, produce what are called exotoxins. And these exotoxins act to do two things. They act to destroy your tissue, and they act to modify the behavior of the host. And so what ends up happening is to make a toxoid vaccine, as you'd imagine, you take this exotoxin, you purify it, you make it into a very, very tiny dose that can't cause any meaningful harm to the human body, and you use that as a vaccination. So what the bacteria normally would do if it becomes infectious, it produces all these exotoxins, and so your immune system recognizes those exotoxins via vaccination. So if you're ever infected with a bacteria, say like pertussis or tetanus, your body will recognize it and attack that bacteria because as the bacteria gets inside you, it produces toxins, and your body will know right away, hey, here's my immune cells that are specific for tetanus. Let's go kill that tetanus as well. And that's a sort of a cool thing. Now, it's typically long lasting. So if you ever got the pertussis vaccination, this is a very long lasting one. Same thing with diphtheria. Other types of toxoid ones like tetanus only last about 5 to 10 years, depending on which vaccination you get. But again, that's pretty long lasting. So if you ever get stuck with like a rusty nail or something like that, you get the tetanus vaccination. Tetanus vaccination if you haven't had one within the past 5 to 10 years. So again, it's a pretty good. Can't cause disease. That toxoid is very, very low concentration, so it's very very difficult to see any side effects from a toxoid vaccination. But unlike our live attenuated vaccinations, they do require several doses, and they also need what we call adjuvants. And adjuvants are, as we'll talk about in a moment, are things that help improve the efficacy of vaccinations. But and then overall, it's a highly effective vaccination, like all these other vaccinations that we talked about. So those are our 4 types of vaccine classes. Again, you'll notice they're all biological in origin. You're not getting chemicals. You're not getting anything else. You're getting just parts of biology. Naturally speaking, it's a very natural process. You're getting exposed to some portion of the organism, very much like you would naturally. So that's what it's working. You're not getting chemicals. You're not getting any crazy stuff. You're just getting small parts of the virus or the bacteria that are safe. Now, as with all science and as with all medical science, there is side effects associated with vaccines. Now, as I've mentioned, vaccinations are very important. They're very safe, but it's important to recognize there are side effects associated with vaccines, very much like there's side effects associated with every medical treatment. So if I take chemotherapy, there's a whole, if I have cancer, there's a whole list of side effects that are associated with chemotherapy, and that's the same for any medication out there. So it's important to understand what the side effects are and how common they are and how potentially deadly they are, to understand any medical treatment and whether or not you should take it or not. Now, the common side effects of vaccination include local swelling, redness, and pain. So if you've ever gotten a vaccination, that's pretty common. It happens to the vast majority of people who get a vaccination because you're having an immune response at that location, and that's in the form of redness and swelling. Relatively common, you get cold light symptoms, fever, chills, headache, fatigue, muscle and joint pain. and these typically disappear within 1 week. The local swelling and redness is pretty common. It's about 50-50 in terms of what redness and swelling. It just depends on the person. These cold-like symptoms, only about 5% of people experience, but again, they disappear within about 1 week. So those are the very common side effects. As you can see, they're very mild. If I get a cold from my MMR vaccine, not a big deal. So pretty common side effects. Now, there are much more rare and much more deadly or potentially life-threatening side effects associated with vaccinations, and they vary depending on the vaccine. So the measles vaccine has much different side effects than, say, the pertussis vaccine. So it just depends on the vaccine. And if you want to know the side effects for any vaccine, the World Health Organization has this really nice set of vaccine info sheets that will tell you what side effects are associated with vaccine, A versus vaccine B versus vaccine C. And so some of the side effects that we see include infections, rash and allergic reaction, as well as high fever. So these happen about 1 in every 10,000 to 1 in every 100,000 people. So those are, infections and rashes and high fever, not particularly damning, but, of concern. Allergic reactions can be particularly concerning, especially if it's a very severe one. Some of the more rare ones include encephalitis, or swelling of your brain, seizures, and potentially death. So, getting the vaccine and you get an infection or allergic reaction that kills you. But those ones, again, those more severe ones are, again, about 1 in a 1 million chance. For instance, the probability of dying from any given vaccine is about 1 in 5 million. So it's very, very rare. If you look at this class, all of you are alive. All of you are probably vaccinated. None of you have died. None of you had any severe reactions to this. So as you can see, many of these are serious, right? Brain swelling is serious. Seizures are serious, but they are incredibly rare. But and so I think it's important to talk about these side effects. They're rare, but they do exist. But again, it's like all medical treatments. They have side effects. But overall, because of how rare they are, because of the benefits of vaccination, the medical community is unanimous in saying that they are safe. But again, there are side effects that you should be aware of. And as with any medication, any treatment in medicine that you do, you should be aware of the side effects. Or any treatment that you try on your own, right? If you're going to try a juice cleanse, which, by the way, the juice cleanses don't work, but if you're going to try a juice cleanse, you should be aware of what the potential side effects of a juice cleanse are. If you're going to try a probiotic, you should be aware of the side effects of those. So anything you put into your body for medical reasons, you should be aware of the side effects. But again, as a whole, there are side effects to vaccinations, but the medical community, scientists, everyone says they are safe. And as I sort of mentioned earlier, there's a lot of bad information out there. There's a lot of potential, side effects out there from vaccinations. None of these are true. Organ disease, autism, cancer, asthma, leukemia, psoriasis, allergies. None of those are true in vaccinations. The symptoms I gave you are true. The previous 2 slides. Those are true, but none of these in this crazy thing you'll see, or things you'll see from people that hate vaccinations, are true. None of these have been medically proven at all. And if it was true, you would see these things at a super high rate in society, right? So the big one people like to say is autism, right? But if you got autism from vaccines, then given the high rate of vaccination in just Massachusetts alone, we would expect to see 90% of people with autism, right? The numbers just don't match up for any of these things. So just as a note, none of these things, SIDS, destroying your immune system, have ever been linked to autism. To vaccination is all. This is just a bunch of pseudoscience and sort of nonsense around vaccinations. But again, there are side effects, and you should know them if you're going to get any vaccination at all. But again, these are not side effects. This is just not true stuff, okay? So with that out of the way, how do we make these vaccines? Now, this is just sort of a really basic tutorial of how it's made. Vaccine Today has a really nice sort of article about how these are made. It's much more in depth than I'm going to tell you, but let's talk about this. So first step, we have to isolate the microbe that we need. So if we're going to make a vaccine against measles, I need the measles virus. So I have to isolate that microbe from an animal, from a human. I have to isolate it from something. Next up after that, I need to enrich the microbe. And I do this by making it infect human cells. So I take a human cell line, which we use in research all the time. And it's important to note it's a human cell line, not human stem cells. It's a human cell line. So an adult donated cells so that we could use in the lab. It's an important thing relative to stem cells. They're a very different class of cells. But adult cell line, you basically infect those adult cells with the virus or the vaccine to essentially increase the numbers of that bacteria or virus that you have. You need a lot of material to make a vaccine from. So that's what we mean by enriching the microbe. Step 3, we need to release the antigen, and this means either we break the microbe apart to get the parts that we need to get the toxin we need to kill the virus or the bacteria, or to essentially weaken the virus or the bacteria. So that's what we mean by release the antigen. We need to make it ready for the vaccination. Next up, we need to purify the antigen from the microbe. So whatever we're going to use to make the vaccine, we need to get that into a very, very pure form. If we're going to give a toxoid vaccination, we just need the toxin. We don't want any other part of the bacteria. We just want the toxin. If we're going to do an attenuated virus, we want just the virus and nothing else. That's it. Once we do that, we purify the microbe. We're going to strengthen the vaccine. And once we strengthen the vaccine, it's approved. It goes through testing and distribution and stuff like that. So one thing important about vaccines is this strengthening part. And this is typically done, and this is done across almost all vaccines, but it's really common in toxoid vaccine. And this is the idea of strengthening. And we strengthen vaccines by adding what are called adjuvants. And so I mentioned this previously, but adjuvants are compounds, pharmaceutical in nature, that modify the effect of the agent, so this microbial part. Now, the idea being is if we have a vaccine against, say, a virus here, we take that vaccine, we inject it into a human, and without an adjuvant, we see no immune response. And this is pretty common. Simply because the virus or the bacteria just doesn't trigger the right immune response. However, when we add an adjuvant, such as aluminum hydroxide or paraffin oil, there are other types of adjuvants, but those are the two most common ones. They basically bind to your microbe of interest, and they make your immune system more likely to see that microbe and thus have an immune response. And so if you want to read a little bit more about adjuvants, I linked the Wikipedia article down here, but that's the idea here. Adjuvants make vaccines stronger. They make vaccines more likely to work. So that's what we mean by vaccine strengthening. And then, as I mentioned, step 6 is approval and distribution. And there's a lot of stuff that goes into that. But one of the important things is, in terms of processing a vaccine, is preservatives. Microbes and the environment vaccines are stored in will degrade a vaccine over time. And microbes will eat anything. They really will. They'll eat a vaccine. They'll eat your dead body. They'll eat leaves. They'll eat your dresser. They'll eat anything. And so we have preservatives, as we do with our food, to make sure microbes don't eat the vaccine. And the vaccine doesn't degrade, say, if it's left out of the fridge. And so we use a number of different preservatives. These include sugars, gelatin, thimerosal. Thimerosal is a mercury derivative. It's only used in the multi-course flu vaccines at this point in time. MSG, so monosodium glutamate. Many of you, if you were around in the 90s, you would have seen the uproar about MSG in Chinese food and other types of food. Completely overblown, but it's a great preservative. And then as well as antibiotics. So they'll oftentimes have antibiotics in vaccines, again, to kill any potential microbes. So those are the most common ones. There are other types of additives they use for preservatives. But in terms of the safety, all these are known to be safe. They're safe if you're not allergic to them. So, if they have penicillin in an antibiotic, well, if you're allergic to penicillin, that's clearly not safe for you. But as a sort of a general note, all these preservatives are safe, including MSG. MSG is safe. There's complete, utter crap around this in the 90s. As the same with thimerosal, again, completely safe. But how do we develop vaccines? And many of you might have been reading about this. If you want to sort of look at how the FDA does this, take a peek at the FDA little vaccination sheet here. How a vaccine is developed, approved, and manufactured varies between country, but here in the United States, all this is approved through the Federal Drug Administration. And they have essentially 3 trials of vaccine, phase 1, 2, and 3, and these differ and their goals, and they differ in their size. And so phase 1 is the smallest, very, very tiny cohorts, 10 to 20 and 10 to 100, sorry, 20 to 100 individuals, to trying to determine, is the vaccine safe? Does it work? Are there any serious side effects? And what is essentially the dose that you need to do? Once you undergo phase 1, you move on to phase 2, with you have several hundred people. And this is where you're trying to suss out what are the common short-term side effects, how are the volunteers' immune systems responding to the vaccine. And so at this point, in terms of the COVID vaccine, they've done many, many phase 1 trials. There are several that have made it through phase 2 and are now moving on to phase 3 trials. In the phase 3 trials, as you can imagine, as the final trial, it is the biggest one, hundreds or thousands of volunteers. How do people who get it compared to those that don't get it? Is the vaccine safe? How effective is it? And what are the common side effects? Because remember, all vaccines have some set of side effects. But once it passes phase 3, the FDA will approve it based upon the science done by the company, and then distribute it for, allow the company to distribute it and manufacture it and pass it out to society. So that's the sort of the workflow here. That's a sort of a simplified version of it. Again, COVID vaccines are in phase 1 and 2. They're starting to move on to phase 3. But these trials take a long time because you can imagine you want these to be safe, right? You don't want a COVID vaccine. You don't want a measles vaccine that has a 10% mortality rate, right? Because that's higher than the COVID death rate, right? So there's all this fact checking and science that is done to make sure they're safe, to make sure they're doing what they're saying they're doing. Because remember, when science is done right, it's life-saving. When science is done bad, it's deadly. So this sort of thing, it might seem like a lot of bureaucratic crap. It's not. It's really designed to make sure things are safe. Now, so that's how many vaccines are manufactured. That's the types. There's the side effects. That's all the background. Let's sort of end this lecture by talking. And I just want to sort of illustrate how easy it is to fall for this. We're going to do a very, very simple exercise. And so I'm going to give you this table. So this is a table. It's from a paper. If you want to read it, go for it. I'll ask you the question, would you eat this? If you saw this list of ingredients of these chemicals, would you eat any of these chemicals? Would you eat eugenol? Would you eat deconic acid? Would you eat beta-acarinol, right? Would you eat an unknown, right? Would you eat this? And I think the vast majority of you don't have to type in the chat or anything, but my guess is if I gave you a list of chemicals, you probably wouldn't eat it, right? I wouldn't. If you gave me this without any background, I'd say, nope, I'm not going to eat that because I'm not sure entirely what those are. And that's important, right? If you don't know what it is, that's a pretty good reason not to eat something, right? Right? If you don't know what a food is, do you want to eat it? No, not really. Yeah, would you really eat unknown number one, Bree? Would you really? But you wouldn't eat these, right? And so this is a bunch of complicated scientific term, right? It's easy to say, well, is gerantyl butynate bad for me, right? It's easy to look at this, not understand what it is, and say, this is bad for me. Now, on the converse, would you eat an apple? And I think all of you would say yes, unless you didn't like apples. But the reality of it is, this is the chemical ingredient list for an apple, right? This long, scary list of things are what make up apples. And so the point of this exercise is not to show you that you don't know what you're talking about or that, chemistry is bad. It's to show you that things can look scary, but they cannot be, right? And, I even as a scientist, I look at this and I don't really know what most of these are. I recognize some of them, but I don't know what all of these are. And so if I just saw this chemical list, I would be wary of it because I don't know what all these are. And I'm a scientist. I've studied chemistry for years. But the average day person looks at these and says, well, should I eat that? And a lot of this happens with vaccination. You look at what a vaccine is. You look at the ingredient list on a vaccine bottle, and you say, do I want this in there? And if you don't know what they are, you say, well, yeah, I don't want that in there. And so the point of this exercise was, again, not to belittle you or anything, like just to show you that list of chemicals, list of scientific things can be scary. But it's important to note that I told you this is an apple. A scientist told you that this is what's in an apple. A doctor could tell you this is what's in an apple. And they know better. And so the idea being is if something looks dangerous, but someone tells you it's safe based upon the scientific method, then that's a pretty good reason to want to trust it. And again, this is an apple. You all know apples are awesome. They're healthy food. But again, chemical apples is scary. So let's talk about stuff that's not true. Let's talk about that in the context of lack of knowledge about the vaccine leads to all these things that are not true about vaccines. Now, as I mentioned, there's a whole series of people try to link to vaccinations. None of them are true, including autism. It's been disproved through small studies and large long-term studies and epidemiological studies. There's all of those things like sudden infant death syndrome, immune rewiring, all that stuff is just not true. There are side effects again, but the ones that people try to link autism, cancer, blah, 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 just simply not true. And that's a thing. Vaccines can make you sick, but again, the stuff that they do is not the things that people are trying to tell you. They're not. You're not going to have your baby die. You're not going to have your immune system wiped away. You're not going to, you're not going to get autism, right? Those just aren't there. There are side effects, and again, if you want to see what side effect for every vaccine is, I gave you a nice FDA link. But all the crazy ones you hear, including cancer, they're nothing. People like to also argue that the infant immune system cannot handle that many vaccines. So you typically, in the United States at least, and as well as Europe, you get a series of 14 vaccinations over about a 3-year period or so. People say that's too much, and that's simply actually not true. So when you actually do the math, if you got all 14 vaccinations you're supposed to get as an infant here in the United States all at once, it would only take about 0.1% of a 3-month-old's immune system to process and handle those vaccinations at a given time. So there's no vaccine overload for children. Your immune system, as I mentioned, it is awesome. It is awesome. It is truly a marvel of evolutionary inventions, but it can handle a lot, and even young children's immune system can handle a lot. So there's no issue with getting a lot of vaccines when you're really young. People also like to say natural immunity is better, but the thing here to remember, vaccination immunity and natural immunity are the same thing. There is no difference for acquiring immunity to measles from a vaccination or getting measles. Because remember, your body's responding to a part of a microbe, and that's all a vaccination is. And if you get exposed to measles, you're just getting exposed to what you were already getting exposed to in the vaccination. But the thing is, getting measles is a death sentence potentially. Getting a vaccine, not likely to have any side effects at all. So that's important. They're the same thing. Natural immunity and vaccination immunity, exactly the same thing. And then sort of the other one of the much more common ones is vaccine contain unsafe toxins. And I put this toxins in quotations because it's not really the right way to talk about this, right? And so there are chemicals in vaccines, and these include aluminum, which is, as we mentioned, is an adjuvant. It's designed to help improve the efficacy of vaccines. Thimerosal used to be a very common thing. It's a derivative of mercury. It is used as a preservative. And as well as formaldehyde, that's pretty common. You'll see very minute quantities of formaldehyde inside vaccines because this is typically what we use to kill or purify the microbe from solution. So these things do exist in vaccines. Now, the important thing to think about here is these sound scary, right? Mercury sounds scary. Formaldehyde sounds scary, right? Formaldehyde is what they use to preserve dead bodies, right? Aluminum, right? It's a metal. It sounds scary, right? But the point here is the context to which they're in the vaccine. So things to remember about these three, which are the most common that are harped upon. There are others, but they're not as harped upon as these three. The important thing to remember here is a couple things. So first is aluminum. Aluminum is the third most abundant element on Earth, and humans, as well as babies and adults, eat greater than 10 milligrams per day. So everything you eat, it's in plants, it's in cows, it's in cereal, it's in everything you eat. Aluminum is so common on this planet, you eat it every day. And you eat about 10 milligrams, upwards of 100 milligrams of aluminum every day with absolutely no side effects. And this is true even in modern times as well as historical times. Again, aluminum is very, very common in the soil. Your average vaccine has less than 4 milligrams of aluminum. So the amount of aluminum clearly is way less than you eat on an everyday basis, and clearly that amount you eat on an everyday basis is not harmful to you. So that's aluminum. Second is thimerosal. It is what we call ethyl mercury. And this is a different type of mercury. We talked about it in the How Science is Done class. But ethyl mercury is not toxic. It's easily processed by your body. It's easily eliminated by your body. It won't cause any harm to you. Now, this is in contrast to methyl mercury. Now, methyl mercury is very, very, very toxic. Very small amounts of methyl mercury can kill you. And this is, again, this is what people are worried about. We're eating like tuna fish and stuff like that. But, or the example I gave you with, Mad as a Hatter, right? That was all from methyl mercury. But the important here is thimerosal is ethyl mercury. It's safe. Methyl mercury is not. And so the form that this mercury is in is important because one is toxic, the other is not toxic. And then finally, we have formaldehyde. And the formaldehyde, again, sounds scary. But again, with formaldehyde, it's really about how much is there. So the average infant has greater than 50 times the amount of formaldehyde in their body from your normally bodily function than you would find in a vaccine. And you get formaldehyde as a byproduct of respiration. As you break down sugars and fats and proteins, you produce formaldehyde. It's a common byproduct, right? So you have more formaldehyde in you on an everyday basis than you do from a single vaccine. So again, it's just the amount that matters here. And for instance, you get more formaldehyde from eating a single apple than you would get from a single vaccine. So again, it's of the amount here that matters. You're not getting enough to cause harm. Now, if you drank a gallon of formaldehyde, or if you drank a cup of formaldehyde, yeah, that would probably kill you. But if you're getting microscopic, minute amounts, it's simply not enough to cause any harm. Because again, you as a person produce more. You get more in a single apple than you get from a vaccine. So the bottom line for here is, yeah, these are present and there are chemicals present, but the vast majority of stuff in vaccinations is biological in origin. And even though some of these chemicals are here, they're not either in the right form, as in the case of mercury, or they're just not concentrated enough to matter. You need grams and grams and grams of aluminum to kill you. You need methyl mercury to kill you or harm you. And you need ounces of formaldehyde to cause any meaningful harm in your body. And so just as a note, these are there, but they're just not enough to cause any harm. And the science is there not only in terms of amounts, but the science in terms of how they affect your body is also there as well. So that's the toxin part. Just to wrap this up, just talk about a few other common things that are not true and misconceptions about vaccines. Vaccines do not give you the disease that you're going to fight. Remember, live attenuated vaccines can do that, but that is very, very rare. Again, it's 1 in 1 million or 1 in 10 million chance. It's not very common. So that's simply not true. If you get a measles vaccine, you're extremely unlikely to get measles from it. People also like to say infections are low. We don't need to investigate. Herd immunity works to keep those infection rates low. Measles is low in the population because of herd immunity. And the herd immunity only exists because of vaccines. But again, many diseases are on the rise again. So we need to keep vaccination going to keep them down. Not vaccinating only affects you and your family. That's just not true. Remember, herd immunity protects everyone. It doesn't just protect you and your family. The decisions you make in terms of public health or global health affect things globally. And this is the same thing for COVID, right? You not wearing a mask doesn't just affect you, right? It affects others as well. And you might not see those effects, but they're there. Another common thing you'll see is that vaccines have human fetal stem cells. That's just not true, especially with the current administration. There's no research being done on human fetal cells because of the position of the current administration on it. But even historically speaking, there's never been human fetal stem cells used in vaccination research. We do use human cell lines, but again, these are cell lines that are donated from adult beings. So nothing controversial here. And even if we do use cell lines, they don't make it into the vaccine at the end of the day. They are filtered out. It's really easy to do. Human cells are huge. Vaccinations are small, right? So it's really easy to get rid of them. And so there will never be human fetal cells in your thing. There'll never be human cells in your vaccine. And then finally, Big Pharma is trying to make money off this. This is what my dad likes to say. And I always like to remind him is, yeah, they do. Does pharmaceutical companies make money off this? Absolutely. But it's not like the money they make off something like insulin or a cancer medication. There used to be 50 or so companies that used to make vaccines. Now it's down to about 12 or 13. I'm sorry, 15 or 16 companies that make vaccinations. And so it's just not as profitable as, say, insulin or, say, cancer medications. So they make money, but it's just not like everything else, right? So they make money. That's not a bad thing. That's how capitalism works. But it's just not a lot of money, right? Every dose of the measles vaccine does not make Purdue Pharma super rich. It gives them a little bit of money as a whole. So with that, actually, I just want to make a note. If you want to read more about this, this article from The Atlantic is really a fascinating sort of read at that as well. So let's wrap it up. Let's talk about what we know. So on-market vaccines are heavily vetted. They're safe. They're tested for years before they're used. Now, the COVID vaccine won't be tested for years, but it will be heavily vetted before it is used. But all vaccines on the market are safe for use, and they're safe for all ages, but they're not safe for everyone, right? If you're immunocompromised, you're pregnant, you can't use them, right? So they're safe for people that they're recommended for. They all have side effects. Most of the serious ones are rare, and so overall, again, they are safe. As I've mentioned, your immune system is awesome. It's the bee's knees, but vaccines are much safer than acquiring a deadly disease. If you want to see how deadly measles, I mentioned I put some slides on Blackboard about measles. You'll learn about measles from these slides. It's a really nasty disease. It is much safer to get much safer to get immunized via a vaccine against measles than to get measles. And that's the same thing for the vast majority of diseases. You don't want to get infected with the tetanus bacteria. You want to get the vaccination against tetanus. Because if you get the tetanus bacteria, you're likely to die. But if you get the tetanus vaccine, you're not going to die. So it's safe. And because these are safe and because they're really effective, they save millions of lives every year. And as we talked about, they have the potential to mitigate this sort of looming antibiotic crisis. And that's important, right? Our healthcare system is already taxed enough by getting rid of by using more vaccines, by limiting our use of antibiotics. It makes us all more safer. It makes our healthcare system run a little bit better. So with that, that's going to be our end of our sort of chat today about vaccinations. If you guys have any questions, please let me know. As always, I hang around for a bit after this is over. But as always, if you have any questions about what you saw today or anything in particular about the course, please do let me know. Otherwise, I will see you tomorrow for our second to last class.